This screencast is one in a series on reactor calculations, and the title is Mass Balance Equations for Chemical Reactors. And the content is chemical reactors and some important types of reactors, aim of reactor calculations, the basis for reactor calculations, the kinetic equations and the mass balance equation, the mass balance equation with the different terms in the equation, some simplifications that can be made and a summary, and finally, how many mass balance equations are needed in order to make reactor calculations. A chemical reactor is simply a system where reactants are converted to products by means of chemical reactions. So in this context, chemical reactor is a very, very wide concept. Chemical reactors may be either engineered or natural, they may be open or closed, they may be mixed or not mixed, or they may be dynamic or at steady state. To give some examples of natural reactors, they could be a cell, a water droplet in the atmosphere, or a groundwater aquifer. They could also be a lake or the atmosphere in itself. I will now illustrate a number of important types of reactors. The first one showed here is a batch reactor, and that is very common in synthesis of pharmaceuticals, and it's also widely used in the paper and pulp industry when wooden chips are boiled as the first step in the production of pulp, and this is a mixed closed system. The continuous flow stirred tank reactor is an open system that is stirred as well, and it's very common in large-scale chemical processes, and it's a natural component in any water treatment plant. Finally, we have the plug flow reactor, and that is also an open system, but it's not mixed, and that is commonly used in gas phase reactors, such as in chemical reactors that are linked to oil refineries, and also in catalytic processes. The aim of the reactor calculations is to calculate the concentrations of reactants and or products in the input flow, the reactor itself, and in the output flow. To be more specific, reactor calculations are used in conjunction with design of chemical reactors to produce a certain amount of chemicals. They can be used to design the hardware in terms of reactor volume and to optimize the mixing conditions. They could also be used to find the right operating conditions, such as the temperature and feed rates. Reactor calculations can also be used to predict the performance of existing chemical reactors. For example, when one wants to utilize a certain reactor for a new purpose. And calculations are often needed in order to predict the response of the reactor to changes in operating conditions, such as the influence of changes in flow rates and input concentrations, etc. And finally, reactor calculations can be very useful when one wants to evaluate experimental data to determine kinetic rate data, such as reaction order rate coefficients. There are two important bases for reactor calculations, the kinetic equations and the mass balances. The kinetic equation is a quantitative characterization of the reaction, and we have one kinetic equation for each chemical reaction. The mass balance equation is the characterization of the reactor itself, and the mass balance is that the input plus the production equals the output plus the accumulation. However, the reactor type, that is, the mixing model, determines which terms that are applicable for a certain reaction. For reactor calculations, the mass balance equations are written with a higher level of detail than for process calculations, simply because the mass balance equations are combined with the kinetic equation. First, some words on notation. Here, for molar flux, I use the letter F. For molar amounts in the reactor, N. For physical flow rates, Q. For reactant volume, I use V, and for chemical reaction rate, I use R. So the terms in the mass balance become, for the input flux, F in, and that could also be expressed in real-life process variables as a product Q in times C in. The production term is denoted F prod, and that can be expressed in process variables as R times V. That is, the chemical reaction rate times the volume of the reactor. The output flow, F out, is quantified as Q out times C out, while the accumulation term, change in number of moles in the reactor per unit time, equals the time derivative of the product C times V. Let's make some simplifications. First of all, if we assume that the flow rate in equals the flow rate out, then Q in equals Q out, which can be denoted Q. Then we recognize that the output concentration from the reactor must equal the concentration in the reactor, and in that case, C out equals C. And finally, if we have constant density or constant volume, the time derivative of C times V, which can be split into two parts, V dc dt plus C dv dt, according to the chain rule, can be simplified to V dc dt, since the time derivative of V equals 0. We can now summarize this in terms of a general reactor mass balance equation. Input plus production equals the output plus the accumulation, so that F in plus F prod equals F out plus dN dt. With the notation and the simplifications we made above, we recognize that Q times C in plus R times V equals Q times C plus V dc dt. And this mass balance equation is valid for all components in the system. In order to calculate the concentration of a certain compound A, which has a concentration Ca, one must solve, first of all, the mass balance equation for A itself, but in addition, one must solve the mass balances for all components in the kinetic equations of the reactions that form A. Let's make this clearer by taking some examples. For example, A yields B with the rate equation K times Ca. In order to calculate Ca, one must solve the mass balance equation for A. In order to calculate the concentration of B, one must solve the mass balance equation for A, but also the mass balance equation for B. The reason why one has to solve the mass balance equation for A is that Ca appears in the production term for B. Here is a more complicated example where A is transformed to B in one irreversible reaction, and B is transformed to C in a reversible reaction. In that case, the kinetic equation for the first reaction is K1 times Ca. The kinetic equation for the second reaction is also first order, K2 times Cb. And the kinetic equation for the third reaction is K times Cc. And here's an error. It should be K3 in the last equation. To calculate the concentration of A, one must solve the mass balance equation for A, but we do not need to solve the mass balances for B and C. In order to calculate the concentration of B, one must solve the mass balance equation for A, B, and C, because B is linked to A via reaction 1, and B is also linked to C via reaction R3. In order to calculate the concentration of C, one must solve the mass balances for A, B, and C. The content of this screencast was chemical reactors, some important types of reactors, and the aim of reactor calculations. Then we discussed the basis for calculations, that is, the kinetic equation and the mass balance equations, and we went into the details of the mass balance equation with the terms in the equation, simplifications, and a small summary. And finally, I had a discussion about which mass balances do we need to solve in order to calculate the concentration of a certain component.